So this is actually a classic problem in fluid mechanics. And what it's asking is the following. So we've got a glass of water, and inside the glass there's a chunk of ice, okay, which can be any shape. And then the question is, what happens to the level of water after the ice melts, okay? So to understand what's actually going on here, we have to look um, at the forces acting on the ice chunk. Okay, so first of all, we have the weight. Okay, and the weight is just the mass of the ice times g, and then we also have this force which is acting upwards. I'm gonna call this force Fp, okay, because this is the force due to the water pressure at the end of the day. So the pressure within a fluid is always acting in all directions, but then when you introduce a solid surface, it's going to start acting perpendicular to that surface, like that, like that. And the closer you are to the surface, the less force you have, okay, because uh, the pressure is proportional to depth. Okay, so once we understand this, we can write the equation of equilibrium. And in this case, we're going to have the following. So the weight of the ice is equal to Fp. Okay, but Fp is actually the weight of the displaced water. And what I mean by that is we're looking here at this volume. So the amount or the volume of displaced water is actually equal to the volume of the submerged ice chunk. Okay, so if I rewrite this, I'm gonna have the weight of the ice is equal to, so the weight of the displaced water is the density of the water times g, and times this basically yellow volume here that I called Vd. Okay, and this is the first thing that we have to find. So we can cancel out the g's, and Vd then becomes m ice over rho w, just like that. Okay, and this is I'll call this one equation 1. Okay, and we'll come back to this in a few moments. And in the second scenario, we have to consider what happens to the water level once all the ice melts. Okay, and for that I will take this to the next page, and let's actually think what happens to this ice, to this chunk of ice. So this is a piece of ice with mass m ice, and it's got a density rho ice. And then after it melts, its mass will stay the same, okay, because mass cannot be created or destroyed. So its mass will be constant, but then its density is going to change, okay, because when the ice melts, it turns into water, and the resulting density is the density of the water, which of course is the same water as we've got in this glass. Okay, so then in the end, after all the ice has melted, the volume of the displaced water is actually equal to the volume of the melted ice, okay, which is the mass, the initial mass of the ice, which doesn't change, divided by the density of the water. So this is by how much the water level will rise in the glass in terms of volume. Okay, so this is equation 2, and equation 1, which was the displaced volume of water due to the solid ice being in the glass, that was equal to the mass of the ice divided by the density of the water. So if you look at those two equations, you'll see that they're actually the same, okay? Which means that after the ice melts, the water level doesn't change. So it stays the same. And I used symbols for this, but obviously if you've got a value of the mass of ice, you can use that instead. The point here is that the numbers themselves, they don't change the problem. Because the displaced volume is always going to depend on the mass of the ice and the density of the water in the glass. Okay? So hopefully you can understand that the volume does not, or the water level stays the same throughout. And this problem actually has a few variations. So another similar problem is the following. So imagine there's like a swimming pool or a lake, and then on that, let's call it swimming pool, there's a boat, and inside the boat there's a person, and also let's say there's a rock. Okay, so I'm gonna call this so this is the rock, and there's a person, and I'm not gonna draw the person, but let's say that the mass of the person and the boat is capital M. So this is the mass of the person plus the boat, and then small m, this is the mass of the rock. Okay, now one key thing to note at this point is that the density of the rock, and this is not hard to imagine, the density of the rock is greater than the density of the water. Okay, because if you throw a rock into a body of water, the rock will sink, and that's because its density is higher than that of water. Okay, right, so the question here is the following: what happens to the water level after the rock is thrown overboard? Okay, will the water level stay the same? Will it go up? Will it come down? So we have to think about it. Okay, so once again, we split this problem in two parts. In the first case, we have the rock and the person in the boat, and the boat is floating. And in the second scenario, we have to look at what happens when the rock is basically on the bottom of the swimming pool and the boat only has the person in it. Okay, so let's start with, let's call it case one. So in case one, we've got so the total weight of the system in this case is m plus m times g, right? And then this is in equilibrium, which means that the force due to the pressure is equal to the total weight. So we can write that m plus m times g is equal to Fp. Okay, so far so good. So this is m plus m times g, and this is equal to, again, this is the weight of the displaced water. And the weight of the displaced water is given by the displaced volume, which is the volume of boat underneath or beneath the water surface. Okay, so that's going to be the density of the water times g, and then times this displaced volume. And as before, we can cancel the g's. Okay, and then the displaced volume is just going to be m plus m divided by the density of the water. And what I'm going to do at this point is actually I'm going to split this fraction into terms. So I'm going to have big M over the density plus small m over the density. And you'll see why I'm doing this in a moment. Okay, let's call this, as before, equation 1. Right, so we sorted out what happens to the displaced volume while everything is in the boat. And now let's consider the second case. So I'll put a 2 here. And in the second case, we've got, so the boat is still floating with a person, with an invisible person in it. And then the rock is now sitting on the bottom of the swimming pool. Okay. Right. So now we've got a different situation. Let's call the displaced volume, let's put a prime just to distinguish it from the previous one. So now the displaced volume of water in the swimming pool is actually caused by two things. It's caused by the boat, and it's also caused by the rock itself. Okay, because now the rock and the boat are in two separate places, so we have to treat those in a slightly different way. Okay, so first of all, let's look at this term right here. So this is the displaced volume of the boat and the person. So for that, we're just going to use our usual balance equation. So that's going to be mg, right? We no longer have the rock in the boat, so we just have mg pointing downwards. And then we've got the force due to pressure. I'll put a prime on it, again, just to distinguish it from the previous one. So then the equation of equilibrium is simply mg equals fp prime. So mg equals, and once again, this is the weight of the displaced water, okay, which is based on how much boat is beneath the surface of the water. So that's rho water times g times vd boat. That's what we called it. Okay, right. So the g's cancel out. So the displaced volume due to the boat, just due to the boat, is the mass of the boat and the person divided by the density of the water. Okay, so that's one thing. But there's also this term here that we need to take into account. So this is actually the volume of the rock. Okay, so the rock also displaces some water because the entire rock is now submerged. Okay, and this is quite easy to find. So the volume displaced by the rock is actually equal to the mass of the rock, which is small m, divided by the density of the rock. So this is simply a case of the volume of the rock being its mass divided by its density. Okay, and I'll call this one 3. Right. So what we have to do now is we have to take those two and we have to add them up and see what happens. Okay, so I'll take this to the next page. Right, so we have two things. So we've got the volume displaced by the boat. This was the mass of the boat divided by the density of the water, and then we have the volume displaced by the rock. That's the mass of the rock divided by the density of the rock. Now, in the first case, when everything was in the boat, we have that the displaced volume of the boat and the rock, everything together, was this, what I call equation 1. Okay, so that is the mass, capital M, by the density of the water plus small m divided by the density of the water. So all we have to do now is just compare those two values. So this one and this one here, and see which one is bigger, because whichever one is bigger tells us in which case there's more water that's displaced, right? Will tell us, effectively will tell us in which case the water level will be higher. Okay, so let's do it in this way. Let's say that I'll do Vd minus Vd prime. okay, and see what I just take the difference of the two terms and I'll see what I get. So this is going to be m over rho w plus small m over rho w. So this is Vd, and I'm going to subtract Vd prime. So Vd prime is actually those two terms added together. So it's going to be capital M over rho w plus small m over rho rock. Okay. Now, if you remove the brackets, the first two terms stay the same, but then you end up with a minus here, like that, and then you can see that two of the terms actually cancel out. So this one and this one cancel out, and we're just going to end up with this term and this term. Okay, so if I write it here, so we've got Vd, so that was the displaced volume in the first case, minus the displaced volume after the rock has been thrown overboard. That is equal to, so we're left with m over rho w minus, that's m over the density of the rock. Okay, so that's m times, so if I just factorize this, this is going to be 1 over the density of the water minus 1 over the density of the rock. And I think we're in a good shape right now, because we know that the density of the rock is bigger than the density of the water. So if you invert those two variables, you'll get that 1 over the density of the rock is actually smaller than 1 over the density of the water, because that's how fractions work. So then if you subtract 1 over the density of the water minus 1 over the density of the rock, this is going to be a positive value. Okay, so which means that this is going to be positive, which means that this is going to be positive, because this is equal positive value, so this is clearly positive. So what we have is that Vd minus Vd prime is actually greater than 0, which means that Vd is actually greater than Vd prime, which means that after the rock is thrown overboard, the displaced volume actually decreases, so the water level goes down. Okay, which in a way makes sense. If you take this problem to a certain extreme, you can understand this at a more intuitive level. So think about it this way. Think of this rock as being the size of a marble, but like really heavy, maybe 20 or 30 kilograms. So then it does displace a lot of water while it's inside the boat, because it drags the boat down. But then when you throw it overboard, its small volume doesn't really do anything, so the water level will decrease. Okay, right, now I want to do another variation of this problem, which is similar to the ice chunk in the glass. So I'll call this one question 3 now. So we've got something like that, and then we've got an ice chunk, and then this is our water level. Right, so we've got an ice chunk sitting inside the glass, and the glass is filled with water up to a certain level. Now, what happens? The question is, what happens to the water level after the ice melts? But there's a twist. The twist is, within the ice chunk, there's an air bubble. So this here is an air bubble. Okay, so what happens to the water level after the ice melts? Okay, well, first of all, let's name our variables like we did with the boat problem. Okay, so I'm going to say that we have a variable named m ice. So this is the mass of the ice itself without the air bubble. And then we've got m air. So this is the mass of the air within that air bubble. Okay? Right. So now that we have this, we can write our balance equation. So we've got acting downwards, we have weight, so that's m ice plus m air times g. And then acting upwards, we've got the force due to pressure. Okay, so if we write this in the form of an equation of equilibrium, we have m ice plus m air times g is equal to, once again, this Fp is the weight of the displaced water. So it's just the rho of the water times g times Vd. Okay, and as before, the g's cancel out, so we'll end up with the displaced volume of water as being m ice plus m air divided by the density of the water. Okay, so that's one thing. And then in the second case, when the ice melts, we have to consider what happens. Now, the ice chunk has an air bubble in it, okay, and this air has a mass m air, we called it, and this ice has a mass m ice. But after the ice melts, what actually happens is that on one hand, the ice, the m ice, gets converted into water, okay, which will have the same density as the water in the glass, but the air is going to escape, essentially. So the mass of the air is no longer going to be a part of the problem from this point onwards. Okay, so then the volume of the displaced water in the second case, it's just going to be the volume of the resulting water, which is going to be the mass of the ice divided by the density of the water, like that. Okay, and this we'll call this 2. Okay, so then equation 1 was telling us that when the ice and the air bubble were floating, then the displaced volume was m ice plus m air divided by the density of the water, right? And then in the second case, we've got this. And you can already tell that Vd is greater than Vd prime because it's got an extra term in it. Now, this is not going to be anything, it's not going to be a huge difference because the mass of air is much less than the mass of the ice itself, but it still makes the volume in the second case, when the ice is floating, bigger than the volume of the displaced water after the ice melts. Okay, so what actually happens with this problem, as you can see, after the ice melts, the water level goes down, and that's it.